Hello and welcome to a video on topic 6 of Edexcel A-level chemistry. This video is going to be explaining points 37, 38 and 39 of the specification, which covers the whole section on alcohols. Within this video you should expect information regarding how to classify alcohols, the reactions of alcohols, and in addition to that, some techniques about how to prepare and purify a liquid organic compound. Anyway, let's get going with how to classify them. An alcohol is an organic compound with this general formula of CnH2n+1OH, with its functional group being right here, known as the hydroxyl group. Alcohols, just like halogenoalkanes, can be primary, secondary, or tertiary, depending on the carbon atom to which the hydroxyl group is bonded. Here's an example of each kind of alcohol down here. As you can see in the primary alcohol, the carbon that the hydroxyl group is bonded to, right here, is bonded to only one carbon atom. For a secondary alcohol, this would become two other carbon atoms, and so on and so forth, with the tertiary alcohol having its carbon atom which is bonded to the hydroxyl group being bonded to three other carbon atoms. That's all you really need to know in terms of classifying them, so let's move on to the reactions. Thankfully, for these reactions you do not need any knowledge of the mechanisms involved, but you will need to know the reactants, products, and conditions involved. Firstly, we can form alkenes from alcohols via an elimination reaction. To do this, you heat a mixture of the alcohol with an acid catalyst, for example, concentrated phosphoric acid. What this reaction does is form an alkene and water molecule from an alcohol. The water is produced from the hydroxyl group and the hydrogen atom from one of the carbons adjacent to the carbon that the hydroxyl is bonded to. In addition to that, EZ isomers can also form depending on which hydrogen is eliminated. With this reaction, a mixture of all possible alkene products and isomers will form. You won't just get one of the possible isomers. And here's an example of a reaction with butanol that I've drawn out. If you get the carbon to hydrogen bond on carbon 1 broken, for example this one here, you'll get the formation of but-1ene. However, if one of the hydrogen on the carbon 3 atom, if the bond there gets broken, for example, depending on which bond it is, you will either get E-but-2ene or Z-but-2ene, and a mixture of all three of these products will form. Now that we've gotten past elimination reactions, we can talk about how to make alcohols into halogenoalkanes. There are different reactions depending on whether you want to make a chloro, bromo, or iodoalkane. To create a chloroalkane from an alcohol, react an alcohol with phosphorus pentachloride. This will produce your chloroalkane, plus hydrochloric acid and phosphoryl chloride. You can also react an alcohol with hydrochloric acid. This will form a chloroalkane and water. This reaction occurs fastest with a tertiary alcohol and slowest with a primary alcohol. The rate of reaction for a secondary alcohol would be somewhere in between those two rates. To make a bromoalkane, react an alcohol with a compound that contains bromide ions. One common example would be potassium bromide. You also need an acid catalyst, which in this case would be 50% concentrated sulfuric acid. This mixture will react in a substitution reaction, where the hydroxyl group is replaced by the bromide ion. This means that the alcohol and bromide-containing compound react to form a bromoalkane and water. Now, if you want to make an iodoalkane, you need a compound called phosphorus triiodide, except if you carried this reaction out as an experiment, you would make this in situ. This means that you would form phosphorus triiodide in a reaction mixture itself, which you would do by refluxing the alcohol with red phosphorus and iodine. I'll explain what refluxing means later, and here's the equation for an example reaction. That's it for forming halogenoalkanes from alcohols, so if you want to know what comes next, we have the oxidation of alcohols, which is a bit more complicated than the previous reactions. The easiest way to oxidize an alcohol is simply by burning it. When an alcohol is completely oxidized by burning it with a sufficient supply of oxygen, carbon dioxide and water is formed. It's that simple. However, if you want to go for a more interesting route regarding oxidizing an alcohol, You could heat it with the oxidizing agent known as a certified dichromate. This solution will normally be orange, and if you oxidize an alcohol, the orange dichromate ion will be reduced to a green chromium ion. This is an important color change that you should note down. When using acidified dichromate, primary alcohols will be oxidized to aldehydes, and then further oxidized to carboxylic acids. Secondary alcohols will be oxidized to ketones, and ketones alone, whereas tertiary alcohols simply will not be oxidized by this. If you want to get aldehydes only, you can distill the primary alcohol, and if you want only carboxylic acids, you can heat it under reflux. If you want to oxidize a tertiary alcohol, you have to do it via combustion. I'll explain what distillation reflux is later in the video, and the diagram on the screen should help you better visualize this. As a reminder, this is what an aldehyde and a ketone looks like, with their general formulae underneath. The C double bond O group is called a carbonyl group, and with an aldehyde, the carbonyl carbon atom is bonded to one alkyl group and one hydrogen, whereas a ketone's carbonyl carbon atom is bonded to two alkyl groups. You can actually do a test to differentiate between a ketone and an aldehyde. This is done either with Benedict's solution or Fehling solution. With Benedict's solution, you heat your sample with the solution. If your sample is an aldehyde, the solution changes from blue to brick red, whereas the solution remains blue if heated with a ketone. With Fehling's solution, there is a color change from blue to red if heated with an aldehyde. It also remains blue if heated with a ketone. The reason why Benedict's and Fehling's solution do not change color if heated with a ketone is because ketones cannot be oxidized further, whereas aldehydes can be oxidized further, and when this is done, they oxidize into carboxylic acids, and in the process of doing so, they reduce the blue copper 2 ions in the solution to red copper 1 oxide, which is a red precipitate. Let's talk about refluxing first. A major issue with organic reactions is that they can have a slow rate of reaction with substances that are volatile and flammable, meaning that if you heat them with a Bunsen burner in a lab, your mixture could evaporate early or even be set ablaze before the reaction actually gets to finish. This is why we reflux a mixture. Refluxing is when you heat a mixture in a round bottom flask with a vertical condenser sticking out at the top. You should be able to see what I'm talking about with this labeled diagram on screen. What this does is continuously boils the mixture, resulting in evaporation. However, the presence of this condenser means that your gaseous reactant will condense and return to the reaction mixture to continue the reaction, allowing completion. Usually you would do this in a water bath or maybe with electrical heating, as this avoids naked flames which could light your organic mixtures on fire. The anti-bumping granules present are added to your solution to ensure that it boils more smoothly. And one very useful application of refluxing would be with the oxidation of a primary alcohol with acidified dichromate, when you only want carboxylic acids to be produced, as volatile reactants would need to be fully oxidized from primary alcohols to aldehydes and then carboxylic acids. A different but also very useful technique would be distillation. Here's a diagram for how a distillation apparatus would be set up. And you need to remember that you should be able to draw these diagrams for both distillation and reflux in your exam if asked to. So as you can see, we have a condenser coming out of the side and a thermometer in the top of the round bottom flask. What happens is you heat the mixture in the flask and the substances will slowly evaporate in an order of increasing boiling point. These gaseous products will then condense in the condenser and then be separated out. This means products with lower boiling points will be produced first, and so on and so forth. The thermometer is so that you know when your product, given that you know the boiling point of it, will evaporate, and that will essentially be when you start getting your product condensing and eventually making its way out of the system. You also need to know why you would want this though, and for that the first reason would be to purify a mixture. You would do this by heating a product if it has a different boiling point to its impurities, and then place a flask under the condenser when the thermometer records a temperature equal to the boiling point of your pure products. Make sure to move the flask away from the condenser when the temperature changes so that you keep your product pure. Another application of distillation is to stop a product that is produced from reacting further, such as when you oxidize a primary alcohol. Let's say you only want the aldehyde. you would have to prevent it from oxidizing further into a carboxylic acid. As aldehydes have a lower boiling point than the alcohol that you start with, it will evaporate and condense the instant it forms, allowing you to collect a pure aldehyde product separately, without it oxidizing further into a carboxylic acid. Another practical technique that you'll come across looking at organic reactions would be separation. Separation is used to separate a liquid that is insoluble in water from a liquid that is soluble in water. This means that you can use it to remove any impurities in your product that are soluble in water in a simple and effective manner. Your separation funnel will look similar to the one you see on screen, and you should pour your mixture into the top with some water as well. Then you should shake it a bit and leave the mixture to settle into two distinct layers. One will be organic and one will be aqueous. After this, you can simply open the tap and allow one layer to run off into a flask, while you let the other layer run off into a different flask. Keep in mind that some traces of water will run off into your organic layer too, and that's completely okay. Most of the water-soluble impurities will be taken away when you decant your aqueous layer off. But what if you want to remove some leftover traces of water from the organic layer you just separated? We can use an anhydrous salt to get rid of the water. Two common drying agents used are magnesium sulfate and calcium chloride. And what happens is that these anhydrous salts bind to the water and become hydrated. This results in the formation of a precipitate after you add the drying agent to the mixture and stir it. You can filter this out using filter paper and a funnel to get rid of the solid precipitate, and afterwards you will have successfully removed water traces from the layer and made it more pure. If you want a rough estimate of how pure your organic product will be, you can do this rather easily using a standard distillation apparatus and figuring out its boiling point. What you do is gently heat the liquid for a gradual increase in temperature, and record the temperature at which the organic liquid has started to condense into your flask. If you compare the temperature you got to the temperature listed for your product's boiling point in a data book, you'll get an idea of how pure the product is by looking at how similar it is. The more impure your product is, the higher your experimental boiling point will be compared to the data book value, and you'll probably have a wide range of temperatures at which your product boils, which further shows the impurity of it. And with that, you are now finished with Organic Chemistry 1. Congratulations, as that is a hefty topic and you'll definitely require some getting used to. What I would now recommend if you want to get better at the topic is for you to look up some past paper questions to consolidate your understanding and apply your newfound knowledge. If you have any feedback, please let me know in the comments, and finally, thank you for watching.